We are studying here thin lens laws. Number 1. The ray through center of lens is straight. It is shown here. The ray through the center of the lens is straight. It is the lens. It is the axis of the optical lens system, and a single ray through the center of the lens is always straight. Thin lens law second. Light rays that enter the lens parallel to the optical axis leaves through the focal point. It is the principal axis of the system. It is the lens, and these are the parallel rays of light coming from the source kept at infinite distance. And this when this parallel beam of light enters through the lens, then this parallel beam of light enters through the lens, then it leaves to the focal point, leaves through this focal point. It is the second thin lens law. Now the third thin lens law is light rays that enter the lens from the focal point exit parallel to the optical axis. It is optical axis. It is parallel to the optical axis, this beam. Then through it is focal point. That light rays that enter the lens from the focal point exit parallel to the optical axis. It is exactly opposite to the second thin lens law. Now applying thin lens law to our object as a gold coin. Here it is the optical axis of the lens system. It is a coin is kept here. Then it passes through this lens. That is a ray from through the center of the lens is always straight according to this first thin lens law. This ray will be here. Now according to second, light rays that enter the lens parallel to the optical axis leaves through the focal point. It is according to second law. Now it is according to third law, that is light rays that enter the lens from the focal point exit parallel to the optical axis. It is optical axis, it is the third ray parallel to the optical axis. Means this ray according to lens 1, thin lens law 1, it is according to thin lens law second, and it is according to thin lens law third. All are meeting at a single point where we can able to have or able to see the image of this same coin kept here. This coin, that is an object kept on the principal axis, on refraction through this system by following three lens laws 1, 2 and 3, we are able to have this image which is below the optical axis. It is the image formation due to thin lens formulae. It is shown here. By a ray tracing convention for optics generally uses arrows to represent the object. It is the object and it is the image according to this by following the three laws. Same three rules can be applied for each point along the object. Means here we are considering the three rays coming from the tip or top of the object. Again we can consider any point of the object. Same rules can be followed and the image, respective image will be constructed on the opposite side of the lens. Thin lens equation. 1 over f is equal to 1 over o upon plus 1 over I. Means in order to calculate the focal length of this particular lens used, it is equal to 1 upon the object distance plus 1 upon the image distance, and the magnification is the ratio of height of the image to the height of the object. It is the magnification. It is the particular formula as thin lens formula for the calculation of the focal length of the lens used in the optical lens system, and it is the formula for magnification, which is the ratio of height of the image to the height of the object. All distances are shown here. The distance from this principal axis of the lens system, it is the focal length of the lens. Then it is from this same point, that is vertical axis, to the object, it is the object distance, and to the right side of this optical lens system, it is the image distance, and therefore this ratio image distance to object distance is nothing but magnification. For an object directly on focal point, rays focused to infinity. Then if we take the another object here which is away from this optical lens than the previous one, then it will be look like this. Again it is from the third possibility, that is three rules to trace three rays. If we replace the convex lens by concave lens, then this case will be here for different rays coming from the object when refracts through the convex lens, then it will be the situation of the rays when pass through the concave lens. Again, two rays enough to locate the vertical image. Here it is the vertical image is observed. Concave lens makes virtual image that is smaller no matter where object is located. Principal ray approach works for complex lens assemblies. Focal lengths act as reciprocals. 1 over f is equal to 1 over f1 plus 1 over f2 and so on up to 1 over fn, where f1, f2, fn all are the respective focal points of that particular optical lens system. Here there is a combination of two lenses. From that, one is convex lens, another is concave lens. After the role of combination of these two lenses, one has able to have such type of images at different points. One is here, another is here. Therefore, it is the first focal length f1, it is the second focal length f2. If we extend this towards this side, then again there are different number of focal points we observe, and one can calculate their respective focal lengths by this formula. Begin with the convex lens. Again we are coming towards this single lens system as convex lens. It is object on refraction through the system. It will be the image. Object is on the axis, image is below the axis. Object is to the left side of the axis, a lens, as well as image is to the right of the side of the lens. The object distance, image distance and focal length all are measured with the rules of optical lens system as according to Cartesian sign convention. If we add a second convex lens here, then there is a possibility of such types of image formation here due to the role of this, because the refracted rays for the first system will be nothing but the incident rays for the second lens in the system, and that will its resultant effect will be observed here, and here that image is formed.